Suppose you're needing to write code that simulates drawing a random subset of elements from a list without any duplicates. If you do a web search to look for an algorithm to do that for you, you'll probably find a web page like this. And if you scroll down to see the top-rated response to this question, you'll see that the very prolific John Skeet lists 3 different methods for doing this. One popular and kind of obvious way of solving this problem is to shuffle the original list. The steps for doing that are listed here, and as you can see in the code, it is linear in the size of the original set, which is good if the subset that you're wanting is approximately the same size as the original set. But if you're wanting a very small subset that's random from your original set, then shuffling is an inefficient way to go about doing it, especially if you just want maybe 3 or 4 items and your original set is 1,000 items. So another approach that John has mentioned and makes intuitive sense is to take one random element at a time. So suppose you take your first random element. Good. Now when you take your second random element, there's a small chance that you've taken the same random element as the previous one. But more than likely, it's a different one. And if it happens to be the same one, then if you use a data structure like a hash set, then when you go to attempt to add it, it will detect that that element is already there, and it won't add it to that data structure. The advantage of a hash set is assuming that the hash is properly balanced. Insertion in a hash set is constant time, and also a lookup to see if an element exists in a hash set is constant time. And so as long as you're wanting to have a relatively small subset of your original set, just randomly picking elements and hoping to get new ones each time is a pretty good approach. But, and then like the third method that John mentions is to say, okay, well, you could always attempt to make progress. Basically, you take your first random element, whatever it is, you're good. When you take your second one, if it happens to be before the first one, leave it alone. If it's beyond the first one, then add one to it. But if you parse through this and look at what it would take to do this third approach, it's an in-log-in average case situation. So this approach is basically a never good. Shuffling is good if your subset is large, and just taking random elements one at a time is a good approach, assuming that your subset is small. But where does that leave us for when the subset is somewhere in between? Not necessarily small and not necessarily big. Okay, so that's the question that I'm seeking to answer, and we have some Python code that I'll go through. And it's not just code. This worksheet is supposed to be illustrative of the idea and the approach and the proof of the strategy of when you'd want to change strategies from taking one random element at a time, hoping to get new ones, and shuffling your original list. Okay, and so I have a bunch of functions here and some matrices, and we're going to use those to understand the transition process of the first approach, of just taking one random element at a time and hoping to get a new one. Okay, and so my first claim, is that state T is a matrix. It's an invalued matrix, which the in this case represents the size of the original set that you're taking your subset from. So the claim is that that matrix represents the transition matrix that represents the probabilities of taking one random element at a time. And so the first column and first rows represent the 0 state. This represents the first state, the second state, the third state, the fourth state, the fifth state. So state T of 5 is basically asking you to imagine that your original set is 5 elements, and you're wanting to take, and you're starting out with no random elements. Okay, so when you go to take your first random element, you're going to be transitioning from not having any to having 1 with probability 1. Okay, suppose you have 1 random element, and you go ahead and you try to get your second random element. Okay, so suppose the first number you picked randomly out of the 5 was the number 2. Okay, and so as long as on this second attempt you get a number that isn't 2, you're good. You have 2 distinct random numbers. If you happen to get 2, then okay, well, you didn't make any progress. So the probability of getting the same one as you did the first time is 1/5. And then the probability of actually getting something new is 4/5. The transition probability of saying that you have 2 items and you're wanting to get a third would be 3/5, and failing to get a third would mean that you picked on your third attempt one of the 2 that you already have previously attained. So this is a transition matrix for sure, because all the columns do sum up to 1. So that is a definition of a transition matrix, and this transition matrix does represent the phenomenon that I'm talking about. And to make it a little bit more explicit, if we were to take state t of 5 and start out with this state vector, which basically says that with probability 1, I have no random elements, and then with probability 0, I don't have 1 random distinct element, I don't have 2 random distinct elements, 3, 4, 5, or 6. Definitely not 6, obviously. Okay, so basically what this represents, this state matrix, when we multiply it on the original state vector, we're getting the next transitioned probability vector. So if you think about it, as I was saying before, if you start out with no random distinct numbers and you go ahead and you take 1, then with probability 1, you have 1 random distinct number. Now, if you apply the probability, if you apply that state matrix to the power 2, so in Python times is to the power, so to the power 2, basically you're applying the matrix twice, then that's going to say that after doing that, with probability 1/5, you're still going to be stuck with having just 1 distinct random element. With probability 4/5, you're going to have 2 distinct random elements. And then after applying it with 3, well, 1/25th probability having 1, pretty small, and then equal probability of having just 3 or hopefully, or sorry, just 2 or hopefully 3 distinct random numbers. So that's what we're looking at here. Now, if you're wanting to know what's the expectation of your distinct random elements in the subset that you're trying to pick through following through this process, well, here, these numbers, what it's looking at is this third case where I have attempted to pick 3 random elements, okay? And so the expectation of doing that is going to just consist of taking one of these vectors, which is, so it's the matrix raised to some power, saying that we have made, in this case, 3 attempts, so this is the number of attempts, multiplying by our original state vector, and then this is our expectation vector. Okay, basically saying that in this state, you're expected to have 0 distinct elements, in this state 1 distinct element, 2 distinct elements, and so on. When you multiply all that out, then your expectation exactly after 3 attempts is 61/25. When you approximate that, it's 2.44. And so if you attempt to have 3 distinct numbers in this process, well, you can't be expected on average to have 3. It's going to be less. And so if you were to run 1,000 trials of doing this process, having 5 elements, taking 3 randomly out of there and seeing how many are distinct and counting them up and averaging them out, it would be approximately 2.44. So that's what the expectation represents. Okay. Now, if we were to bump this up a bit, this is just slightly different notation to make it easier for us to see it. But this is still thinking of our of having 5 random elements. And so suppose that we have 5 random elements and we take 5 attempts. Okay, so 5 random elements, 5 attempts. The expected number of distinct elements that we're going to have is about 3.336, which is definitely less than 5. And basically what this is saying is if we know we're wanting to find a subset of random elements that are more than 4 elements, so more than 3.36, then it's going to be more efficient for us to go ahead and do the shuffling algorithm. But if we're wanting 3 or less elements out of a set of 5 elements, then theoretically it would be more efficient on average to go ahead and just take 1 random element at a time. Similarly, if we have 10 random elements and we make 10 attempts out of those 10 random elements to get distinct elements, then on average we'll find 6.5 random elements. And so once again, basically that's saying that if we're wanting a subset of 6 or less out of the 10, we should go ahead and just take them one at a time, hoping that they're distinct. If we're wanting 7 or more, then we should do the shuffle algorithm. And you can see, so this is the same thing with 15 and 20. You can see the growth here is approximately linear. And so we're going to come back to that. I think that's a very interesting phenomenon. We've observed it empirically, and we're going to see that actually rigorously pretty shortly. Okay, and so now, and actually, you know, in the original question where we are asking, well, where's the cutoff point? What is the strategy for deciding when to take random elements one at a time, hoping that they're distinct, versus shuffling? So I just told you an algorithm. You know, basically, you know, you have these matrices, you have these vectors, you can do this arithmetic. So say that, you know, your original set is of size n, your subset is of size m. You can say that you can have, you know, put your n here, do n attempts, which, why is it n attempts? Well, basically, this is telling you, you know, how many random numbers you're expected to get, and the shuffle has an expectation of n, right? So that's why we're doing it this way. And so, you know, an algorithm that would actually answer the question would be to say, okay, well, our original subset is size 20, so let's put 20 into this algorithm. Okay, we get about 12.83. All right, so is our subset that we're desiring greater than or less than 12.83? If it's less than, do one. If it's greater than, do another. So there's an algorithm. Problem with this algorithm is that doing these matrix multiplications is extremely inefficient, right? So if every single time we were trying to figure out what's the cutoff point between doing the shuffling behavior and doing the just taking one at a time behavior, if we had to compute this every single time, it wouldn't be efficient. So the question is, can we find the expression for these in a relatively cheap and fast way? So that's what we're trying to do. Okay, and so if we represent this state transition matrix in a slightly different way, we're going to be able to achieve that. And so this is what I'm showing you here is the Jordan canonical form of the state transition matrix. So once again, we're considering the case where we have 5 distinct random elements, and I've introduced 3 more matrices. And so you'll notice that we have this P matrix, this D matrix, and this PI matrix, which I'm claiming is an inverse. When you multiply them all together, you'll notice that we got the original state transition matrix. And then you'll also notice that D is a diagonal matrix, and that when we take these outer matrices and multiply them together, we get an identity matrix. Okay, so when we have these three properties with a diagonal, two inverses, and we're able to multiply them together and get a matrix, then that says that we have a Jordan canonical form of that original matrix. And what's interesting about the Jordan canonical form is that it allows us to do this very expensive part of exponentiating a matrix in a simple way. So let me show you what I'm talking about. Okay, let's see. All right, so I don't have it here. Let's go ahead and insert a cell. Yeah, so I'm going to insert a cell below. And let's say we have state t of 5 to the third power. Okay, so state t of 5 to the third power is relatively complicated. It's not a cheap thing to do. Okay? But what's kind of nice, a nice property about the Jordan canonical form of a matrix is that exponentiating a Jordan canonical form is the same thing as exponentiating just the diagonal part. Okay, so you'll notice that taking the state matrix to the third power is the same thing as only taking the diagonal part to the third power and then multiplying by those outer matrices. And the reason why that's cheap or that's nice or cost effective is when you raise a diagonal matrix to the third power, or to any power for that matter, it remains a diagonal matrix and it's just the original entries raised to the power in question. Okay, so that's going to be the strategy that we're looking towards. And basically all that I've done right up to this point is to just show you empirically with one particular example of this Jordan canonical form and why it would be interesting and why it would be useful. And so now my claim is that these functions up here and these matrices up here actually rigorously represent for all n a representation of this transition matrix. And so in order to prove that, well, it's pretty clear that this D matrix is diagonal, okay, because I'm saying if I equals j, return something. If I does not equal j, be 0. Okay, so we've satisfied one criterion already. That's not hard to show. And so really what I need to do to rigorously prove this representation is, one, prove that p and pi are indeed inverses of each other, or in other words, when you multiply them by each other, that you get the identity matrix. That's one. And then the other thing is to show that in general, when you multiply these three matrices together in this order, regardless of n, you get the original state transition matrix. So that's what I need to show. In order to do that, let's go ahead and look. We'll start with this step. So I'm going to prove that these two outer matrices multiplied together is the identity matrix. And when you are multiplying matrices together and you're trying to find the terms for those expressions, it ends up being the sum of this, something like this, basically, where you throw in a dummy index variable k, and on your first matrix you put k in for j, and on your second matrix you put k in for I. And when we multiply that out and let this worksheet simplify it, this is the expression that we get. Okay, and so the terms for this multiplied matrix, or these two matrices multiplied together, is this assuming that we sum from k equals 0 up to n. Okay, and so how do we get a general form, a closed form for the sum of this from k equals 0 to n? Okay, so there's a really nice tool for that. I like Gosper, which is a function that's in this really nice and old, I think the oldest computer algebra system called reduce. And so if we take this expression, plug it into here, and do this indefinite sum, out pops this expression. Okay, so it's kind of magic, right? We get an expression. If we're trying to prove something rigorously, if we just get an expression and I assert that this expression actually represents the sum, then I haven't really proved anything super rigorously. But what's nice is that basically what we found is an antidifference. And so I can actually confirm that whatever algorithm they use to find this, that this antidifference expression for the sum of these terms is actually a correct representation. So if we copy that into here, then to verify that it is an antidifference, in other words, that this expression right here represents the closed form of taking the sum of these terms, all that we need to do is take the antidifference and then evaluate what it would be, taking one lower index, taking their difference, and then looking at one individual term inside that summation and seeing what we get. And so to show you that I'm not pulling the wool over your eyes, if we were to actually plug these things in and just print it out, that's what we get. And then this comp simp method basically converts all the factorials and Pochhammers and gammas into one unified representation and then simplifies them. And basically what we find is we get 0. And so this is, in fact, a rigorous approach to show that this is a antidifference for the sum of these terms. And what's really cool about that is that if I evaluate the antidifference at the endpoints of the sum, n and 0 in this case, and take their difference, it's equivalent to what this sum is. So if we were to sum over this and figure out what it would be, it's going to be the same as this. And now, if we look at it, we notice a few things. So one of the things that we notice is that we have j and 0 here. And so whenever we have a binomial, whatever comes first has to be greater than or equal to what comes second, or that term is 0. So what this term right here is saying is that this whole expression is 0 unless j is 0. But if j is 0, then this part of the expression is 0. So this whole expression is 0. And so basically what that is saying is that whenever this antidifference is valid, a valid representation for this, for the sum of these, those terms are going to be 0. And that antidifference is valid basically everywhere that I is not equal to j, everywhere that that denominator is not equal to 0. So as long as I is not equal to j, the terms sum out to be 0, which is what you would expect from an identity matrix. Okay, so suppose that I does equal j. So if I does equal j, so if we come back to that, what we'll end up finding is we are summing from k equals 0 to n, where of binomial I choose k times binomial k choose I when I equals to j. Now, if you remember what I said before, this term, in order for it to not be 0, would say that k has to be less than or equal to I. But if j is I, then this would say that k has to be greater than or equal to I. And so when we're summing from k equals 0 to n, if I equals j, the only possible non-zero term is the term of k equaling I. So if we evaluate k equals I and j equals I into this sum, you clearly get after simplifying 1. All right, so we've proved the first part. We've proved that in general, regardless of n, state p times state pi is the identity matrix, and so these are indeed inverses. And so now we just need to verify that these three matrices multiplying by each other is in general the state T matrix. Okay, so we're going to take a very similar approach that we just did. Okay, so we're gonna start off slow. All right, so there's three matrices that we're multiplying by each other. The first thing we're going to look at is state P times state D, and we're going to try to figure out what that is. Okay, so what we're looking at is the state P element. So this is the element representation for the state P matrix, and this is the element representation of the state D matrix. And we've kind of done a few silly things here. We have a summation, and normally we would expect to see I, K, K, J. So why do I have J, J in this summation from K equals J to J here? Well, it's because D is a diagonal matrix. Okay, if we go to the definition of D, then if I equals J, it equals J over N to the power M, but in this case M is 1. Okay, so it's just J over N. All right, so with a diagonal matrix, basically what that's saying is that if K is not equal to J, it's 0. So the only time when we're summing from K equals 0 to N that we're not getting 0 is when K is J, and so this is the general form of the elements of the resulting matrix from multiplying these two matrices together. Okay, so now if we're trying to do the same thing, finding the resulting form of the three matrices being multiplied together, then what we'll need to do is take this same guy right here, plug it in, and we will replace J with K, and then multiply the third guy replacing I with K. Okay, standard thing. So those are the Jordan terms, and if we evaluate, or if we just display the Jordan terms, this is what it simplifies out to be. Okay, and so we are interested in knowing what this looks like summing from K equals 0 up to N. All right, we're going to use our friendly Gosper tool again. So if now notice I didn't put everything in here. I only put the terms that depend on K in here. So we have -1 to the I plus K, we have K, we have binomial I choose K, we have binomial K choose J. So we have all that. I didn't put these last two terms in because there's no K. Just a quick note, if you ever do use Gosper, make sure that you remember that I represents the square root of -1. And you don't come into that problem if it's just a regular index to one of these special functions. But if you have -1 to the I and then you try to do this, you might be led astray and get a crazy looking expression that's not true, which is a mistake that I made, so please don't make that. But what you can do is just replace the variable. So I replaced I with A, no problem, and lo and behold, something nice. Okay, so basically just took that anti-difference expression and put it into here. And once again, you have the expression. You take what it is when you substitute K with K minus 1, you multiply the terms that you're interested, or you subtract off the terms that you're interested in, and then when you go ahead and do the combinatorial simplification, 0. Good. Okay, so this is a valid anti-difference representation of this nice thing, right? Of the terms of these three matrices multiplied by one another. Okay, and so now if I'm wanting to have a closed form representation of this being summed from k equals 0 to n, then I just have to take their antidifference, evaluate it at n, and evaluate it at 0, take the difference, and simplify, which is what we did. Okay, so when we do that, what do we notice? Okay, well, we have binomial I choose n and binomial n choose I. So these two terms together are saying that if I does not equal to n, it's for sure 0. But if I equals n, then this term right here says it's 0. So once again, for this particular antidifference function, wherever the antidifference method is valid, the terms sum out to be equal to 0. Okay, so where is it valid? Well, it's valid whenever the denominator is not 0. And remember, A in this case is I, and the denominator is valid whenever I is not equal to j, and whenever the denominator is not equal to I equals j plus 1, which is great. That's exactly what we see when we look here, right? So this is I equals j, this is I equals j plus 1. So we've proven so far that all these guys are 0 and all these guys are 0, not just for n equals 5, but for all n. So now we just have to look at the diagonal, these two diagonal terms. Verify that. Okay, not a big deal, because if we take the Jordan terms, evaluate I equals j, print it out, what I can show to you is that we have, and so we would have to sum this up from k equals 0 to n. But we have binomial j choose k and binomial k choose j. So every single term is going to be 0 unless k equals to j. So summing from 0 to n is the same as just plugging in j for k. When we do that, we get j over n, which is correct. That's exactly what we want to see. If we plug in j plus 1 in for I, print it out, what we're going to see is binomial k choose j. So that's saying that k has to be greater than or equal to j. And we have binomial j plus 1 choose k. So that's saying that j plus 1 has to be greater than or equal to k. So basically that's saying that unless k is equal to j or j plus 1, the terms are 0. So summing from 0 to n is the same as plugging in for j and j plus 1. If we plug those in, do a combinatorial simplification, lo and behold, we get this. And if we look at the original definition of the state T matrix, we do have j over n, and after simplifying, 1 minus j over n. So good, we've verified that that expression, that Jordan canonical form expression is correct. Okay, so sorry for scrolling around so much here. Help you keep track. So once again, why was that useful? Well, if we're wanting to take the state transition matrix to some power, then all we have to do is look at what happens when we take the D matrix to a power. Okay. So expression for the terms. Oh, this is not correct. Sorry about that. We will fix that later. Okay, so the Jordan power terms. The only difference here is that, well, it's basically the same thing that we did to get the Jordan terms, except we have to take our diagonal elements and raise them to the nth power. Okay, so so this DE elements, if you remember, we had this m, and so in general we have j over n, and when we put the n here, then it's j over n, both that whole term raised to the nth power. Okay, and when we plug this in, print out the Jordan power terms, we get basically the same thing that we had before, except this small part, instead of being a 1, we have k over n up to the nth power. Okay, so this is just, once again, this isn't the full thing. What we would have to do in theory is sum this up from k equals 0 to n. And that would give us the general form of what it looks like when you take the state transition matrix up to the nth power. Okay. Unfortunately, if you go to Gosper and you try to plug that in, if you plug in 2 for n and 3 for n and 4 for n, it can find a closed form expression, but it cannot find one, and it can actually prove it will actually prove to you that no such closed form expression exists. And so, fortunately for us, we don't actually need that. Ultimately, what we're wanting to compute is the expectation of how many distinct elements we're getting after having that state transition matrix being applied n times. Okay? And so the expectation, have gone ahead and used this a variable, and basically what it's going to say is that if we have 0 elements, then our expected number of distinct elements is 0. 1 elements, the expected number is 1, so on and so forth. This inner matrix represents the probability of being in that state. So this sum is the probability of being in the state. This represents the number of distinct elements, so the value of being in that state. So if you sum over the values times their probabilities, you get the expectation. So that's what we're wanting to compute. This, as it's written, is rather hard to compute. However, we can do a trick. So one nice thing about expectations is they tend to be easier to compute than the original thing itself. And that manifests itself here by switching the order of summation. So if we take this a inside the inner sum, and instead of summing with k first, we sum with a first, then we can get a really nice simplification. Because while we can't get a closed form expression over this k index, we can get a nice closed form expression, and I have another instance of Gosper open, over if we look at the a index. Okay, so we have this anti-difference part here. Now notice, once again, I didn't put this full expression into here. I only put the terms in that have a in it. Okay, but okay, what do we have? Well, we have, presumably, I'm claiming, an anti-difference of taking the a in the inner sum and summing from a equals 0 to n. Okay, so let's verify it. We have what I'm claiming is the anti-difference, and we take the a index down by 1, take the difference, and then subtract off a. So where's the a? So we have a times, yeah, basically a times the Jordan power series terms. Okay, so this is the sums. This is what's inside that first sum. Basically, all of these terms inside here is the Jordan power series terms. This is the a that we brought inside. Now you'll notice that I plugged in j equals 0. So that seems like a tricky thing for me to be doing. Why did I plug in j equals 0? Well, when we multiply the expectation vector, so we're multiplying that vector from the left. Okay, so you take the expectation vector, you multiply from the left, and when you do that, basically you're only going to be looking at the first row of the resulting matrix, multiplying, let's see, Okay, so all right, so we have this outer sum. This is computing the this is the expectation part. You can think of this part, this sum, or maybe, yeah, this part is a little bit easier to see. So you can think of this as the sum, or you can think of this sum as the state transition matrix times that initial state transition vector. If you left multiply that by the expectation vector, which is just 0, 1, 2, 3 all the way up to n, then basically you're going to be pulling off of the j equals 0 column. So that's why that's there. Okay. Very good. So when you take that difference, you get 0. And so now basically so this 0 right here is proving that the anti-difference that we found is valid. And if we're wanting to bring the a inside and sum from a equals 0 to n, it's the same thing as plugging in for a and plugging 0 in for a, taking their difference, simplifying it, we happen to get 0. So what is that saying? Basically it's saying wherever this anti-difference is valid, all the terms sum up to 0. Okay, where is it valid? It's valid whenever, okay, and in this case, oh, sorry, not that one. It's valid whenever k is equal to n, or sorry, it's valid whenever k is not equal to n and whenever k is not equal to n plus 1. Okay, very good. So if we go back to this original sum and remove k going from 0 to n and just plug in k going from n minus 1 to n, which is what I do right here, going from n minus 1 to n, evaluating a for I, j equals 0. You print out those terms. This is what you get. And when you combinatorially simplify it, you get this expression. So presumably, this is the expression of the expectation of the distinct number of elements, assuming that you have n elements and you make n attempts of getting distinct random elements. All right. And to just do a sanity check, just to verify whether or not we should actually believe that this expression is correct or if it makes sense, let's just consider two simple cases. Suppose that n is 2. So our original set is 2 elements, and I want to get some distinct elements, right? So after my first attempt with probability 1, I'm going to have 1 distinct element. On my second attempt with probability 1/2, I'm going to get a new element. Okay, and so my expectation of the number of elements that I'm going to have when n equals 2, doing 2 attempts, is 3/2, which is what we're getting from here. Okay, let's say that n equals 3. So we have 3 elements, and I take 3 attempts at getting distinct elements. Once again, our first attempt is free. We're for sure going to get one. Now, with probability 2/3, I'm going to get a new one on my second attempt. Okay? That's just what it is. Now, on the third attempt, if I did get a new one, meaning on my third attempt I'm starting with 2 distinct random elements and I'm wanting to know if I'm going to get a third random element, well, I'm in that state with probability 2/3, and with probability 1/3, I'm going to get a new distinct random element. Okay, so that's this part. If in the third attempt I started with 1 distinct random element, which means in the second attempt I didn't get a new one, well, that happens, by the way, with probability 1/3. In that case, well, with probability 2/3, I'll get a distinct random element, and I get with the expectation 19/9, which agrees. So, yeah, empirically, this checks out, it makes sense, and if you go back through all the steps rigorously, this indeed is the expression for the expected number of distinct elements that you would have if you started with n elements and you made n attempts. Okay, and if you remember from before, what I was saying is that it looks like that expectation grows linearly. And so if you take that expression for the expectation and you divide it by n, and you take its limit as n goes to infinity, and subtract off 1 minus exp of minus 1, you get 0. Basically, I'm saying that this is just a fancy way of saying that the limit ends up being 1 minus exp of minus 1. And if you approximate that, it's approximately 0.632. Okay, which, if you go back up, 0.632, when you multiply by 5, is very close to that. 0.632 times 10 is very close to that. 0.632 times 15 is very close to that. So we actually get pretty fast convergence for relatively small values of n. Okay, that's really nice. And so now we have this constant. What are some neat things we can do? So if we look a little bit more empirically, let's say that we are going to do 1,000 trials and we have 1,000 elements that we're interested in picking from. And let's say that we're wanting to pick 632 elements distinctly out of that set of 1,000 elements. What's pretty neat is that, okay, if we run this, 0.632, or this 1 minus exp of 1 times 1,000 is approximately 632. So that's why we have the 632. What I've done here is I've multiplied this by 1 out of a million, which is taking into account 1,000 trials times 1,000 out of our size, out of our set. So that's why that division is there. And okay, so yeah, it converged almost exactly to 1. Now what's even more cool is if you add 3 to it. So if you just go one more above what this theoretical limit should be, then it goes beyond 1. And you can repeat that every, that works really nicely. And so empirically, there's a very low variance of what you would of deviations of what you're expecting to get when you use this constant as the break point for when you're going to decide to use the shuffle algorithm versus the other algorithm. Okay, so basically for 1,000 elements, it makes sense that after 632 elements, if you're wanting to have a random subset, you might as well go ahead and shuffle it. One possible application that I'll just kind of put into your mind, maybe I'll look at it sometime in the future, is that because this has a very low variance, you could actually use this methodology as a strategy for finding a coefficient of randomness. Okay, so if I were to take, or if I were to make a biased random variable, which I could do by just saying, okay, take numbers in my range, take a random number in my range, another random number in my range, multiply them together, and then take their square root, I'm still going to get, okay, in this case, if my range is from 0 up to whatever my number is, which, okay, so I'm cheating a little bit, but so assuming that the range is from 0 up to some number, if I do this biased rand range, then I'm still going to have a random number from 0 up to my exclusion point, right? But it's not going to be a uniform distribution. And if I do the same thing, so just for the sake of being able to run this trial fairly quickly, instead of doing 1,000 elements, I ended up doing 100 elements. So 100 times 0.623 is approximately 62. But I mean, if you used a faster computer or maybe use more optimized code, you could take this out further and really see that, okay, if you truly had a uniform function that's going to give you random numbers, then because you have that low variance that I was showing you before, then you could have a fairly reliable measure of randomness. And so this is actually detecting the fact that it's exceeding 1, which, if I don't use a biased one, if I go ahead and just use the normal rand range, okay, so that's 0.95. If I do 6.3, it's 0.98. Yeah, if you just use an unbiased one, then you're getting much closer to 1. So that could be a way of looking at random coefficients, another possible application. So the overall code, here's a standard implementation of the shuffle code. Assuming that you don't actually care about the order that you're getting this random subset in, if you go ahead and use set in Python and just keep adding elements, this is a reasonable approach to go about doing that. And as you can see, this implementation of get random elements, if you pass in a list and you say how many elements you're wanting randomly as a subset of the original list, well, we hard code in our special constant that we found, and then this basically says, do you want to do the shuffle method or do you want to do the other method? So I mentioned the caveat about if it falls into this case, the order that you get back the elements in this particular implementation is not completely random. Another thing to know about the shuffle in this particular implementation is that it actually mutates the original list. So if you're okay with mutating the original list, you can go ahead and use it this way. If mutating the original list is going to be problematic for you, then go ahead and just copy the list, shuffle the copy, take a subset out of that, and that will work for you. And so just an example of using the code, using the algorithm, if you're just wanting to take 5 random lowercase letters out of the alphabet, oh, there you go. So not really sure I have the rest of this here. Okay, well, so that's the explanation of the algorithm of trying to take a random subset of distinct elements out of a list. You have those 2 different behaviors, and this is a nice strategy right here to decide when to do one versus the other. Thank you very much for listening.